Welcome to the UGC EPG Pathshala lecture series in computer science. In this series of lectures, we have been looking at data management system. And for today's session, we will be looking at the continuity of multimedia indexing. Some of the learning objectives for today's session include, we are about to introduce another level of tree structure which is called MX Quadtree, which will be a continuation of point quadtrees. And we will try to understand the procedure of insertion and deletion to these MX Quadtrees. Not only that, we will go for another level of advanced trees which will be called R trees. We have some advanced trees associated with this like AVL trees and so. But for the discussion of this particular session, I will stop with R trees, which is supposed to be region trees. And we will compare the performances of all these 4 trees at the later half of this particular session. So, to define on the node type of MX Quadtrees, the node structure of MX Quadtree will be something like this. So, expand the node structure of Quadtree node type to a new node structure which is new Quadtree node type, where Quadtree node type is a record, information as info type, X value and Y value are real. So, until this the procedure is very common with the point quadtrees, but then to be very specific on the MX Quadtrees, it will be on the X lower bound and upper bound, where X lower bound, Y lower bound, X upper bound and Y upper bound, which has got real from minus infinity to plus infinity. And as we say it is a quadtree, we have the same directions into impact, which is northwest, southwest, northeast and southeast, which are defined by the pointers to the quadtree node type. So, when we expand the node type that is represented here, when inserting a node n into the tree T, we need to ensure that if n is the root of the tree T, then the lower bound should be minus infinity, X lower bound should be minus infinity, Y's lower bound should be minus infinity, X upper bound should be plus infinity and Y's upper bound should be plus infinity. So, that means from minus infinity to plus infinity on Y, minus infinity to plus infinity on X. So, if the parent P of node n, then the following table describes what n's X lower bound, Y lower bound, X upper bound and Y upper bound field should be, depending upon whether n is to the northwest, southwest or northeast and southeast child of P. So, we use a simple notation called W, which indicates P dot X upper bound and P dot X lower bound, and the difference of H, which is indicated by P dot Y upper bound minus P dot Y lower bound. So, here we use the notation W to find out the difference between the X values of upper bound and H for identifying the difference between Y values of the upper and lower bounds of the same parent node P. There is not much of a difference when compared to the point quadtrees that we have discussed already. It was the difference only with the limits that we have identified here. It was between minus infinity and plus infinity. In the previous case, we have never indicated the values as such. So, when deleting an interior node n, we must find a replacement node R in one of the subtrees of n, that is in one of n dot nw or the node dot southwest or the node dot northeast or the node dot southeast, such that every other node R1 in n dot nw, that is to the northwest, is the northwest of R. Every other node R2 in n dot sw is to the southwest of R. Every other node R3 in node northeast is to the northeast of R, and every node R4 in n dot se is to the southeast of R. So, whatever node like R1, R2, R3, R4 that I am trying to insert, which clearly indicates me that I am deleting a node R1 which is present in the northwest of R. I am deleting a node which is present at the southwest, simultaneously I am deleting at the northeast and southeast. I am appropriately finding the location from the map where exactly it is being located and trying to replace that node with some other node or deleting the complete node. If in case I am not able to find an appropriate replacement node, then there is an impossibility of finding a replacement candidate. Thus, in general, deletion of an interior node n may require reinsertion of all nodes in subtrees pointed to by n dot ne and n dot southeast, n dot northwest and n dot southwest. In the worst case, this may require almost all nodes to be reinserted. So, anything that wants to be replaced, there may be worst cases where all nodes have to be replaced in case if a specific node in the exact tree is to be deleted. As we have seen to the two-dimensional trees, range queries in the two-dimensional trees, now we will look at the range search in our point quadtrees. So, each node in the point quadtree represents a region. Do not search regions that do not intersect in the circle defined by the query. We have a procedure of range query point quadtree which has a new quadtree node type, and we may have to define the circle also with the radius. If region of T intersection circle is empty, then we may have to halt. Else, if T is x value and T is y value being an element of the circle, then print the x value and the y value. Range queries point quadtree will have T dot nw comma the circle's radius. Range queries point quadtree will have southwest with the circle, northeast with a circle and southeast with a circle. So, that shows the procedure of how a range search has been done with the quadtrees, point quadtrees for both. In case of MX Quadtrees, for both two-dimensional trees as well as point quadtrees, the shape of the tree depends upon the order in which the objects are inserted into the tree. So, the level of the tree or the height of the tree is dependent on the order in which we try to execute, because as I have talked about, if the level of the node is even or the level of the node is odd has been searched for, and alternatively we have been performing the left horizontal cross section or vertical and horizontal cross section in the two-dimensional tree, and in the point quadtrees we have been doing both together, whereas in MX Quadtrees it is not the same. So, in addition, both two-dimensional trees and point quadtrees split the regions into either 2 or 4 point quadtrees with those sub-regions. However, the split may be uneven depending upon exactly what the point n dot x value and y value is located inside the region represented by the node n. Whereas, same is not the case with MX Quadtrees, where we define the infinite limits, that is ranging between minus infinity and plus infinity. So, MX Quadtrees generally attempt to ensure that the shape, that is the height of the tree, are independent of the number of nodes present in the tree as well as the order of insertion. Maybe it is not completely dependent on the order of the node, whether it is even or odd. MX Quadtrees also attempt to provide efficient deletion and search algorithms. Assume that the map being inserted is split into a grid size of 2 power k into 2 power k for some k. The application developer is free to choose on the value of k if he or she likes to reflect the desired granularity. So, as finer granules that I would like to give, I will have more enhanced details of that particular location. But once he or she chooses the value of k, he or she is required to keep it very much fixed. Then it is there is a possibility that this might come to a point quadtrees again. When we wanted to define it into finer granules, that means the order of k should be more, then we get the maximum granularity. So, this table represents the complete node structure in terms of 2 power k, exactly the same as point quadtrees, except the root of MX quadtree represents the region specified by lower bound as 0, upper bound as 2 power k, and y's lower bound should be 0 and y's upper bound as 2 power k. When a region gets split, it gets split down in the middle of that particular region. Thus, if n is a node, then the region represents by 4 children of the node n with the directions as northwest, southwest, northeast and southeast. So, the 4 children are represented here, northwest, southwest, northeast and southeast. The x lower bound would be n dot x lower bound, n dot x lower bound plus w by 2, where w is the parents' difference of lower bounds on the x value, and southeast will be n dot x lower bound plus w by 2, and same is for the upper bound. With upper bound it will be the other way around your northeast and southeast. For northeast and southeast we have a lower bound clearly defined with plus w by 2, whereas for the children of northwest and southwest we have lower bound defined as w by 2. And for the y value we have northwest and northeast, that is the upper half of the region is being divided and the lower half is being divided for, that is for southwest and southeast it is for w by 2. So, this is a simple tree structure that is being plot for an MX quadtree, where we have got all 4 points. Say for a location of a of x comma y, if I wish to insert a specific node, then if it is to the say northwest of a specific parent, then that node gets inserted, and the subsequent node that I am supposed to insert, if it is to the northeast of the subtree, then it is branched to the northeast of this particular node. Likewise, I can insert a specific node which need to be on the northeast of a specific node, that is branched here, but I see one other node which is located to the northeast of this specific node, but there exists another node, and to the northeast of that, then B is inserted to the northeast of the root node. It finds another node that is available, then it is to be inserted to the northeast of that specific node. So, that is how it goes and the tree structure evolves. But when we try to compare between 2-dimensional trees and MX quadtrees, the height of the tree is getting largely decreased as the boundary limits are clearly defined. Say upper bound and lower bounds are clearly defined, in that specific juncture the height of the tree is completely decreased. So, after the procedure that we have looked at earlier, after insertion of a, say a point, initially there was a root node which is divided into northwest, northeast, southwest and southeast. Now, when I have inserted a point A which is split into 4 quadrants, after insertion of point B which was to the northeast of the root node, so that has been divided into 4 quadrants. After insertion of point C, that is to the southeast of the actual loop, and after insertion of D, that is to again to the southeast of this node. So, what lies as a procedure for deletion in MX quadtrees? So, deleting an MX quadtree is fairly simple operation because all points are represented in the leaf level itself. So, if n is an interior, that is a non-leaf node in the MX quadtree whose root is pointed to by T, then the region implicitly represented by the node n contains at least one point that is explicitly contained in the actual tree. If we wish to delete a point x comma y from tree T, we try to preserve this property. This can be done as follows. First, we set the appropriate link of n's parent to nil. So, the parent of the node that is to be deleted will be set as nil. We then check if all 4 links of that particular m are nil. If so, we examine m's parent. let us call that as P. As M is P's child, we find a link field dir1 such that P dot dir1 direction 1 is equal to M. We then set P dot dir1 is equal to nil, and then check to see if all 4 links are made clearly nil. If so, we continue this process, or else if there is found to be a specific node which is branched from that particular node, then we cannot delete that particular node. So the total time required for deletion is O of k. So we may have to check for all subsequent nodes that are routed to the actual node. We have to make that nil initially so that we can branch it, or we can make this particular node delete. So this is handled in exactly the same way as we have handled it for the point quadtrees, but there are 2 differences when compared to point quadtrees. So here we have introduced the MX Quadtrees, we have introduced the lower bounds and upper bounds, whereas there we have not introduced so. So the content of lower bound, upper bound, lower bound or upper bound of x and y coordinate fields is different from that of a point quadtrees. So as points are stored in the leaf level, checking to see if a point is in circle denied by the range query needs to be performed only at the leaf level itself. So far we have seen 3 different trees. One is on the 2-dimensional tree, point quadtrees and MX Quadtrees. Now that we have been understanding on the procedure of only the points that were located on the maps. What happens in case if I am to mark that as a rectangle instead of a point? So a point is just about a circle, and how large I make this point counts. So if in case I am making it as a rectangle, so we used to store the rectangular regions of an image or a map such that in such a way that it is shown here. So R trees are particularly useful in storing very large amounts of data on disk. Say when I map or when I mark a rectangle of a specific region, then it exactly means I am marking an entire location, which means that it takes up a large data space of mine, so that it takes all those pixel values. So they provide a very convenient way of minimizing the number of disk accesses. Say specifically I have gone on a point, I have marked on a specific point. On a specific point when I am operating with, there might be a possibility that I might miss out on specific interested regions that can be very near to those that are specified, but marking as a rectangular region will not eliminate those specific points. So this increases the performance of the entire tree structure. So each tree that is associated in this order will have an integer k. Each non-leaf R tree node contains a set of at most k rectangles and at least k by 2 rectangles. Intuitively, this says that each non-leaf node in R tree, with the exception of root, must be at least half full. This feature makes R trees appropriate for disk-based retrieval. So whenever I wanted to have a shorter period of retrieval, then I will appropriately access on the disk, and the time in which I am accessing that gets reduced, because of each disk access brings back a page containing several or at least k by 2 rectangles. So R trees manipulate 2 kinds of rectangles, either it could be real rectangles or it could be a group of rectangles. Here comes the example of an R tree, where here I have indicated a group of rectangles called G1, G2, G3, and this group in turn has some real rectangles called R1, R2 and R3. I have identified specific region with a rectangle. This rectangle is grouped together. Say I have marked several rectangles like this, which are found to be clustered, and after marking all these clusters, this can now be grouped together under one particular node. So this R tree is of order 4 associated with the rectangles. This is need not be 4 of in terms of order, it can be even more than that, but then we have identified 4 groups here. So, we will say 4 nodes, order of 4. So, R tree nodes has the following structure. RT's node type is assigned as a record, and we have rectangle 1, rectangle 2 and rectangle K, which are specifically mentioned as rectangles, and P1, P2, P3 until Pk are the R trees node type. So, now understanding on the procedure of deletion in R trees. Deletion of objects from R tree may cause a node in the R tree to underflow, because R tree of order K must contain at least K by 2 rectangles in it. So, when we delete a rectangle from R tree, we must ensure that node is not underfull. That means it is not the same procedure as we follow with the MX Quadtree, where we make all the elements of that particular node as null, all the directions as null. Instead, it should not be less than 2. Say when we have started defining the order of the leaf or the root node as 4, it should not be underfull where it is, where we have only one rectangle associated with the group. So, it is underfull where we compare it with the order of the actual root node. So, let us try to understand the procedure of deletion in this rectangular trees. If we delete R8, then the node containing rectangle R9 would have only one node in it. Say in the group 3 that we have assumed initially, in the group 3 that we have here, if we delete R8, then it will have only R9 associated with group 3. In this particular place, this has this, as we say, this is underfull. So, in this case, we must create a new logical thinking where we have to transfer some of the nodes associated with the other groups to the node that we are considering it, or the group that we are considering it fresh. So, one possibility is to relocate some of the groups and relocate some of the rectangles to the existing group, so as to make it not to make it underfull. Assuming that we have got 3 groups G1, G2 and G3. Supposingly we have R1, R2, R3 which are associated with group 1, R4, R6, R7 which are associated with G2, and R5 of G2 has been taken out and it has been assigned with R9 of G3, so as to make it not under full constraint. Now, this will become the new node structure where R5 and R9 are found to be very close proximity to each other. So, we will assign these two under one specific group after having deleted R8. So, R1 and R2, R3 exist as such, R4, R6, R7 becomes another group, R5 and R9 which are of close proximity when compared to the proximity that we had in the earlier group, then we will consider this as a new group. So, when we understand on the procedure of this rectangular trees, it is not on the point that we are trying to concentrate with, rather it is on the rectangle. So, when we plot on the rectangles, the distance between two different, there is a large difference between two different points and two different rectangles which are mapped together. When we had only points, the distance between the 2 points has been computed based upon some distance calculation like Euclidean distance and so. Now, the distance between two different rectangles where it could be of close proximity. So, that could be one of the logical thinking that we will have, so as to group it with the, so as to branch it with the other group. In this example, as I have indicated, R5, although it is assigned with group 2, but then we have seen with our logical level that R5 closes or matches very closely with R9, since not because of R8 has gone from the loop, so that we wanted to avoid the entire group, but because of the reason that R5 and R9 are of close proximity. Say for example, when we draw a structure, say in the south, when we compare two different regions like Mahabalipuram and Chennai, Mahabalipuram and Pondicherry, at one particular location for say tourism places, Mahabalipuram and Pondicherry might be two dominant places. So, supposing that I wish to add Mahabalipuram very close proximity to Chennai. In that specific juncture, R5 is supposed to be Mahabalipuram and R9 is supposed to be Chennai. For that reason, R9 need not be deleted, having deleted some other like Kanchipuram and so. Having deleted Kanchipuram, that does not mean that I have to delete complete of Chennai or miss out complete of Chennai. So, Mahabalipuram can be the other location which can be taken from the other group. So, this location has been considered to be of very close proximity to this location. So, R9 and R5 are closely related in order to avoid this underfull category criteria. So, in short, in this particular lecture, 2 sessions together, we have started indicating on the need for multimedia indexing, and we have started talking about multidimensional data structures. So, we have started with KD trees, and then we have assigned the order of K as 2, which is 2-dimensional trees, and we have started plotting the tree structure of the 2-dimensional trees, and we have talked about the insertion deletion operation of the 2-dimensional trees. It was all binary. Then we shifted ourselves to a point quadtrees, where instead of dividing the entire region or the entire point into left and right links, how would it be, or how can we improvise on the time constraint or the access to the storage. So, in that specific case, point quadtrees limited by itself, dividing into vertical and horizontal cross sections by directions northwest, northeast, southwest and southeast. Not only that, we had an extension of point quadtrees, which is MX Quadtrees, where we have defined the lower bounds and upper bounds from -infinity to +infinity on both the x and y values, whereby we have decreased on the number of disk accesses and we have decreased on the time that we were about to process considering a specific region. And finally, we talked about R trees, which is supposed to be region trees, which had group rectangles and which had real rectangles. Clustering some of the real rectangles formed a group rectangles, and we have made sure after every deletion or insertion procedure is very common. So, any node that is to be inserted, we will check for which rectangle is closely related to what group, then we will try to put it in that particular group by defining a specific order. But then when it comes to deletion, we will make sure that this node is under full. So, when the node is under full, we put up a logical thinking that all other remaining rectangles in that particular group need not be deleted. For that specific reason, we will try logically shifting some of the real rectangles to the newly formed groups. So, by where we will try to have so many rectangles as such, and we will try to proceed it from there. Thank you.